You know, we hear it all the time. Quantum computers are going to change the world. But for years, they've been kind of stuck, hitting this single massive bottleneck. Well, we're here to talk about a stunning breakthrough that might have just smashed that bottleneck wide open. I mean, just imagine for a second, what if we could design life-saving drugs in a few days instead of decades? Or create materials with properties we've only ever dreamed of? This isn't science fiction, you know? This is the real-world potential of a full-blown quantum computer, a machine that could tackle some of humanity's absolute toughest problems.
So, let's talk about that promise. What is it, really? It's all about unlocking a completely new way of calculating things, one that gets down to the fundamental and, frankly, weird rules of the universe.
And these promises, they're not just some abstract ideas. We're talking about the power to design super-specific drugs, molecule by molecule, to literally invent revolutionary new materials that can do incredible things. Oh, and yeah, to break the very encryption that secures our entire digital world. The stakes? They couldn't be higher. But there's always a but, isn't there? And this one's a huge one. To actually get the answer out of a quantum computer, you have to listen to individual atoms. And, well, that's turned out to be a massive, massive challenge. To really get why, let's look at the basic building block. A classical bit, right? Like in your phone, it's either a 0 or a 1. That's it. Simple. But a qubit can be a 0, a 1, or both at the same time, thanks to a wild thing called superposition. Now, that's the secret sauce that gives it exponential power, but it's also its greatest weakness. It makes the qubit incredibly fragile and really, really hard to measure. So, one of the most promising ways to build these computers is with arrays of neutral atoms. This approach is fantastic for scaling up. I mean, we're talking thousands of potential qubits. But it has always had this one nagging critical weakness. And that weakness is what's known as the readout bottleneck. Imagine this. You just ran a massive calculation on thousands of qubits. Now what? Now you have to accurately measure the state of every single one of them, all at once, and do it incredibly fast. For a long time, that's been the brick wall. Physicist John Simon has this brilliant way of describing why it's so hard. He says it's like trying to listen to drunk particles scattering photons haphazardly. The signal from a single atom is just so faint, and it goes in every direction. Trying to catch that tiny signal for thousands of atoms at once, it's been a total nightmare. But what if you could give every single one of those drunk particles its own personal amplifier? Well, that's where this ingenious solution from Stanford comes in, the Cavity Array Microscope. So what is this thing? Well, in a nutshell, it's a completely new kind of optical system that gives each individual atom qubit its own dedicated amplifier. It's like taking that faint, chaotic whisper from the atom and using a tiny, perfect megaphone to make it signal perfectly clear and easy to read. And the advantages here are just huge. First off, it's incredibly fast. We're talking millisecond timescales. Second, it's non-destructive. This is so important. It means you can check for errors and repeat measurements without having to reset the entire calculation. And third, and this is the real game changer, it's parallel. It measures all the qubits at once. Okay, so how does this thing actually work? The magic is in some incredibly clever optical engineering that literally gives each atom a voice of its own. It basically breaks down into 3 main steps. First, you trap and isolate the atoms in a neat little grid. Then, you use a custom microlens array. Think of it like a sheet of thousands of tiny, perfect magnifying glasses to focus light onto each atom. And finally, here's the secret sauce. Each atom is placed in its own tiny optical cavity, a little space between 2 mirrors that traps and amplifies its faint signal like crazy. So you isolate, you focus, and you amplify. And you know, this isn't just some small improvement on an old design. As postdoctoral scholar Adam Shaw puts it, we have developed a new type of cavity architecture. It's not just 2 mirrors anymore. Integrating these microlenses is a fundamental leap forward. Okay, so they've solved this huge problem. What does that actually mean for the future? Well, this is where it gets really exciting. We could be talking about the dawn of actual quantum networks. And look, this isn't just a theory on a whiteboard. The team has already built a next-gen prototype that scales to over 500 of these individual cavities. This shows that the technology isn't some one-off lab trick. It's designed from the get-go for massive scale. And the jump in performance is just staggering. The old way of reading qubits, one by one, was painfully slow. This new parallel method is orders of magnitude faster. What that really means is we can finally run deeper, more complex quantum algorithms, the very kind that were impossible before because we were just waiting around forever to get the answers. This kind of speed and scalability opens up a whole new vision for what's next. John Simon imagines what he calls quantum data centers, basically modular quantum processors, each with one of these fancy new interfaces, all networked together to create a massive distributed quantum supercomputer. But you know what? The implications go way beyond just computing. Being able to efficiently catch the light from a single particle is a holy grail in so many fields. This could totally revolutionize biosensing, letting us detect the faintest signals from individual molecules. It could even help us take incredibly high-resolution pictures of distant exoplanets. The possibilities are just mind-boggling.
So here's the bottom line. By solving one of the most stubborn, frustrating bottlenecks out there, this cavity array microscope has potentially unlocked the path to truly scalable, networked quantum systems. Which really just leaves us with one big question, doesn't it? Are we finally, truly on the verge of the quantum era?